Bring up. Oh, it hasn't started yet. It's just coming. It takes a minute out of sync or so.
Oh, okay.
It's coming now. It's just coming. It takes a minute out of sync or so. Okay. It's coming. So you're playing back.
Yeah, I just muted. Okay.
So this is, I think you're playing, you have two screens open. One is the playback, and then one is, so you can get rid of the playback screen and then keep the sharing screens. Maybe.
So how do I do that?
So keep this one. Do you have any other browser session open, like your Firefox? Yeah, get rid of that one. Yeah, that's Firefox.
Wait a second. I'll download that one. So close that.
Is there any other browsers? Maybe this one. Yeah, close that one. Yeah. I can do one more test.
Okay.
Testing 1, 2, 3.
Yeah.
Okay, good to go.
Yeah. Okay.
Just make sure your screen.
Okay. Let's see this. Yes. Okay. Is everyone ready? Okay. So my talk today is on the use of digital logic in RF circuitry, particularly signal processing. It follows on from the last talk that I did a few months ago on quadrature. The original motivation was to use a spectrum analyzer, the 10 megahertz intermediate frequency output of a spectrum analyzer, and then find a convenient means of demodulating the signals that so effectively using the spectrum analyzer as a radio receiver. One of the best ways of doing that was to down convert in quadrature, which also means that I can quite easily visualize the modulation constellation on an oscilloscope using the X and Y plot settings. So this might seem like a bit of a step if you haven't actually listened to the first talk and briefed up on quadrature, but Kasim did a pretty good job of refreshing us on that one. So I'll just move straight into it. As I said, so you're in phase and quadrature allow you to reconstruct the phasor, amplitude, and phase. So one of the sort of simplified, more common diagrams is this one up here showing the edge-triggered D flip-flop, where the clock frequency triggers the top flip-flop on the rising edge. They're both triggered on the rising edge of their incoming clock, but you see there's an inverter which actually causes the lower clock to trigger on the downward transition. And then you see here the 90-degree phase shift that results from those two outputs of the flip-flops. And then here is just a refresher on how that fits into the architecture of a down converter. And just like to point out at this point that when you're mixing and you're down converting, you end up with a lot of harmonic content. So the idea of these low-pass filters is to remove anything above baseband that isn't actually the modulated carrier. So you're talking about harmonics, either harmonics from the clock input, which is quite relevant in the use of digital logic for driving oscillators, and also the higher order harmonics as a result passing through the nonlinear elements of the mixer. So it might be a bit of a stretch. I've done the best that I can to chop these images down to make them manageable. This is just a schematic showing a more detailed implementation of what you saw on the previous slide with the D flip-flops. But I've added something here. I've changed something in the core use of the D flip-flops, and that is that in the let's go back. In this one here, you see the use of an inverter, and that's not absolutely necessary because quite often the D flip-flops have an output which is differential signal, where you've got the complement of the status of the D flip-flop. So you don't need to use an inverter, which minimizes the propagation delay and then the skew of those clocks out of ideal 90-degree phase. So, and then we have one clock here driving these two clock transitions. One is inverted, one is irregular. And the thing to note with a D flip-flop when it's driven by the clock and it's latching the data in on each positive clock transition, and sorry, I made a mistake there. That's pretty bad, but at least I got it on this occasion. So the complement of the status of the D flip-flop is meant to be fed back into the input, such that on each clock transition you have a toggle. That's what I stuffed up, so never mind, I'll have to fix that up. So the complement is normally fed back into the D, which means that on each rising transition you have a toggling of the state of the flip-flop. What that also means is that the flip-flop is effectively a divide by 2. So if you want a 10 megahertz out, you've got to give it 20 megahertz. And the use of this flip-flop down here is sort of dual purpose. It provides the complement, but it also ensures 50% duty cycle. And you can't necessarily guarantee a 50% duty cycle from your oscillator. Depends how it triggers and exactly when. I mean, the only thing that an oscillator really guarantees regularly is the frequency, if you're lucky. So yes, this gives us 50%. This gives us quadrature, but this effectively becomes a divide by 4. So your input frequency is going to be divided by 4. So if you want 10 megahertz out, which is the case for a 10 megahertz intermediate frequency down converted to baseband, you need a 10 megahertz signal. So you need a 40 megahertz clock, which comes in from below here. But we'll move on to the next image, and you'll see where these signals sort of get routed around the schematic, and also like a practical and close-up look at how it's implemented in integrated circuit packages.
How was it divided by 4?
Because, yeah. So each edge-triggered D flip-flop in a toggle arrangement is divided by 2. I've cascaded 2 layers. The other important thing about this is to note the blocks where I've used this method of converting a 5-volt. So I should probably give you a bit of a description about the considerations given to logic families and the timing. I didn't have time to put it in the slides, but I can tell you all about it here. Because we will be driving, generally speaking, when I design logic, it is best to go for a family that supports 3.3 volt and 5 volts, just to give you the flexibility to change the system depending on what accessories you might have connected, whether or not the clock gives a 3.3 volt, a CMOS output, or a 5 volt. For my purposes, and up to about 150 to 200 megahertz, depending upon the actual integrated circuit, 7.4 AC series are pretty universally good. If you want to go above that, you've got to go to LV. I think LV. But I'm actually aiming for a higher voltage because I'm going to be driving these coax lines, and you want to maximize the amount of power that you can deliver to a mixer. And there are a few issues in appropriately terminating coax. So when you terminate the coax, you've got a 50 ohm resistive termination. And when launching into coax from logic, you need to ensure that you don't present a short to the logic gate, because at high frequencies, effectively, that's what a coax line is a short on the logic. So you need to look at the maximum deliverable current per gate, and in this particular package, the 74AC14, the maximum deliverable current source or sink is 50 milliamps. So you obviously don't want to meet or exceed that. If you look at a 5 volts into a short circuit, well, actually, you want to be able to launch into coax using a resistive termination to minimize the reflections and impedance mismatch. So you're looking at 50 ohms effective resistance between your coax and the logic gate. At 5 volts, that's 100 milliamps. So if you use a single gate and you're driving a 50 ohm resistor into a short, you're going to be trying to pull 100 milliamps or source 100 milliamps, which exceeds the specifications of the 74AC14. So what you can actually do is you can parallel the gates in such a way that they don't short into each other or into a load, but they share the source or sink current load. And you do this by paralleling the resistor combined with the gate. And by paralleling the 350 ohm resistors, you end up with 50 ohms effective resistance. And then each gate is driving around about 33 milliamps, which is well under the specified limits. The other thing to be concerned about there is the concept of fan out. So when driving CMOS logic, when it's a short, well, CMOS logic is effectively FETs, and FETs are voltage-driven devices, or there is a capacitive gate on the FET input, which means that when you change the transition of a FET, you have to charge or discharge a capacitor, which is effectively a short circuit. So there is a limited amount. Sorry, it's a short circuit at very high frequency AC. So there's a limited number of gate inputs you can drive from one output, and that concept is called fan out. So you need to make sure that the picofarad limit of that output is not exceeded by the sum of the gate input capacitances. And then, of course, we use a ceramic capacitor to provide DC blocking, because we don't want 0 to 5 volts, we want plus minus. So it's an unbalanced sinusoid transmitted about the ground reference. So that allows us to break the DC path. And that's about all I have to say on here, other than, of course, these flip-flops, when they have complementary outputs, you don't just get 0 and 90 degrees, you also get 180 and 270, so it's not a lot of extra effort to pull those out, and they provide a lot of useful signals for whether or not you want to run a phase lock loop on one of them, or you want to run one of them into an analyzer or a counter. So for the additional effort, it made sense. And here is the actual implementation. So it's a bit scabby. The quality of my prototyping varies depending on what hour of the morning I'm doing it, how many things I've broken, and how many things are left to not break. What's important is to ensure you have continuity of ground plane first and foremost in, I'd say RF prototyping, but digital as well, to preserve the integrity of the signals, particularly when you're driving square waves. People think, well, 10 megahertz, 40 megahertz, 100 megahertz isn't much, but they might be forgetting about the harmonic content that can stretch up into the gigahertz. So yeah, continuous ground plane. And actually on a number of these, I've used a ferrite combined with a capacitor to try to minimize the EMC released, and also to try and keep a handle on how that propagates throughout the rest of the circuitry, because there are a couple of critical references which could be done a lot better, but when I had the time, I was doing it. So yeah, this is laid out more or less as this is, so I tried to keep them as similar as possible to easy understanding. There's a little oscillator down here, which is just a fixed frequency test oscillator. It's not really that important, it's not used at this point. And here are the signals in quadrature, so you can verify them. The other important thing to note is when you're reading signals on an oscilloscope is typically a high impedance load, so you need to terminate to ensure the signals are read correctly without ringing. Okay, so
in this case, when you would be reading those as a transmission line, it would affect the reflection stuff in the transmission lines anyway, right? Even if you properly terminate your...
Yes. However, you've got to look at the load impedance of the scope, and typically the scope is sort of like 1 megohm. So you'd probably get more of an impedance mismatch from the T-piece than you would the scope itself. Yeah. And we're going up to maximum of 80 megahertz on the top test oscillator, 40 megahertz on the voltage-controlled crystal oscillator, but the harmonic content is there up until probably just sub-gigahertz, I'm guessing. So there was a slide that I wanted to put in here, but I had to dig it out of textbooks and reference it and everything. But that is the architecture of phase lock loop. So this is going to be slightly winging an explanation of the phase lock loop. Now, if you would like to lock the oscillator to the carrier frequency, you need a way of doing that. That's effectively a phase lock loop. Not just a phase lock loop, but a phase frequency lock loop. And the frequency lock is, of course, secondary to having a phase lock. If you've got phase lock, then presumably you've got frequency lock too. It's just being pedantic. But in order to compare two signals, we'd like to digitize them. So at the moment, the signals are varying amplitude, and the best way to do that, or the quickest way for me to do it, was to do a zero-crossing detector. So here comes a coax in. There are two zero-crossing detectors because we're comparing two signals. You isolate the DC, and then you basically, so this is a 5-volt supplied system. So I'm basically putting a reference at 2.5 volts and saying that, sorry, the reference is here. And at 2.5 volts, this is relatively, well, it could be stiffer, but that's, we just kind of assume now that that's 2.5 volts on the negative sides of those comparators. So if the presented signal causes this point to swing, either side of that reference, it's going to register as being above or below it, and put out a 1 or a 0 respectively for that zero crossing event. This particular comparator, your comparators are relatively expensive to get high speed. If you're talking about tens or hundreds of megahertz, you're going into sort of $5 to $20 something for a comparator, which is a bit ridiculous. And that's only because they're expected to operate very, very quickly. So to clean them up, I've used some Schmidt triggers, just because they were available in another package that I had to use for the phase lock loop. So this squares up the signals. They come out of here. It's sort of triangular, not very nice, and the timing of those is pretty critical to ensuring you have a stable phase lock. From that point on, we can move to the phase frequency detector now that our frequencies have been digitized. And this is a sort of more component-specific implementation of what you would see as a kind of logic diagram for a phase frequency detector, a digital one anyway. There are a couple of different ways of doing this, but we're sticking digital for now. So effectively what this is a who's first, if you want to put it into human terms. Which clock rises first detector. As soon as there's an upward transition on either of these clocks, their respective flip-flop will enter the high state and output a 1 on their Q line. And as soon as either of these, as soon as both of these are triggered, both will be cleared. That's basically an English way of explaining this. So it's a race to see which one will trigger the flip-flop first. And then when the other one catches up and then triggers, then they both get reset. And what you end up with is an output signal here, which is proportional to the amount of phase that is overshot and undershot, or the difference between the two signals. So you have a proportionality measure, and you also have a polarity measure. So you know if you should be driving your oscillator higher in frequency or lower in frequency. Then you effectively have an integrator here, and you can source current. So if you want to drive it in one particular direction, you source current into this capacitor. As soon as that signal disappears, your capacitor should just hold the charge, right? So nothing should happen. If you wish to discharge the capacitor, you can trigger this current sink, and that will sink current out of that capacitor and linearly decrease the voltage across it. So what you end up with is effectively a phase-controlled integrator, and that integrator will then control the frequency drift of your oscillator. So then this signal should normally be passed through a low-pass filter. I didn't have time for it, and it still seems to lock within a narrow range, so I moved on to doing the presentation. Here is the zero crossing detector. There's a whole bunch of jibber jabber there. Unfortunately, you can't see the detail. And then this is the Schmidt trigger. This is the D flip-flops. And here is the rather ghetto charge pump. Yeah, sure, okay. So where you see all these little black transistors is the charge pump, and it got hacked around because I tried a few different things. What you see in most of the literature is they sort of optimistically show a switch. I think this is just to be intuitive, and they say, well, okay, you know, if you exceed this threshold, or sorry, if you trigger one of the flip-flops, then flow current through here, and if you enable the other one, discharge current out of it. The actual implementation is a little bit not that simple, because as soon as you start trying to use analog bilateral switches, which is what I did, I thought, well, okay, this is how you do it. There's a propagation delay on the activation of bilateral switches, and it turned out to be not fast enough. And it's cheaper and easier and lower impedance to just chuck a few transistors in. So although this talk is on digital logic, this is actually the better solution, despite it looking rather messy. And then these funny little resistors coming out here, that's just to ensure that I don't exceed the voltage control specification on the oscillator. But effectively, where those two resistors stick out and join the white wire is now our control voltage for driving the trim on the crystal oscillator. And so coming up the bottom right-hand side of the screen, bottom right-hand corner, is the frequency trim voltage, and that is a simplified representation of the voltage-controlled temperature. Sorry, voltage-controlled temperature compensated crystal oscillator. So I got that acronym wrong as well. It should be a VCTCXO.
You actually did more saying that.
Sorry.
Contrast to you did more saying it.
Yeah, yeah, it's all in there somewhere. Yeah, so and different oscillator classes have different pull abilities. This particular one is designed to be a sort of an instrument reference, and as such, I think the pull ability is 116 parts per million per volt. So over 10 megahertz, that's what, 7 kilohertz or something, is that right? Yeah. So if you think about how much a carrier can drift, let's say, for example, if you're observing Doppler shift, that's not going to be good enough, right? Because your Doppler shift might be a few kilohertz. So really, like, I've got to find a better oscillator. There are VCOs which are, they have a sort of octave range. So their frequency can go between, say, like 10 megahertz and 20 megahertz, or 50 megahertz and 100 megahertz, but that's still a bit too wide. So anyway, the common emitter amplifier was just to boost it because I didn't read the data sheet. And this is a lesson. In reading data sheets, you should ensure that to minimize the amount of time that you spend dicking around, match the output of each device to the input of the next device. Like, yeah, that's just me being hard on myself, but then you don't have to muck around with that kind of stuff. And here on the sort of more copper-looking board is the TC, whatever it is, temperature compensated voltage controlled crystal oscillator, and then the amplifier. So that's not particularly interesting. Okay. So this is the full schematic, which I know you can't see from there, unfortunately. Maybe people on the web can if they're lucky. So we'll just move on. So that's the whole thing in its entirety, but there are a couple of devices that are external to it. So mixers, power splitters, low pass filters. So this is kind of zooming out. So there you can see, if I go back, what I will explain in this slide, because it's a little bit crucial to understanding this piece, well, it's not a PCB, but this circuit board, in the greater context, what you have is an oscillator that generates quadrature. That oscillator is then fed back in to, well, actually, let's start from the carrier reference. So you've got 10 megahertz reference. It comes in on the left-hand side. That's fed in as a reference to the phase-lock loop. So you can't adjust that, right? That becomes the reference. What you can adjust is your own oscillators, right? But that effectively becomes the reference for the phase-lock loop. Then it gets taken around the top, and it gets fed into a power splitter. That power splitter, it's not very good. It's a 6 dB resistive splitter for wideband use, but then that gets fed in as the RF path on both mixers. So there's a mixer on the left and a mixer on the right. That gets mixed with the local oscillator input on the mixer, which is driven by the quadrature oscillators. Then the output is at intermediate frequency. That's important to get the ports on the mixer right, because the intermediate frequency allows you to extract a DC component. So that helps you very quickly and easily identify whether or not you have phase lock, because the DC component is going to be DC and not some wandering beat frequency. And then, yeah, one of the signals from your local oscillator is fed back in as the feedback loop on the phase lock loop. Okay, so that gives you a little bit more context as to what's happening here with all these flying leads about the place. The top one in the middle is that's the 10 megahertz in. So it's the 10 megahertz intermediate frequency coming in. And then the top left and the top right are two low pass filters for ensuring that you remove all the harmonic content from the mixing process and the square waves used to drive the mixers. There we go. So move on to a video, and I hope this is visible on the streaming and the recording. Oh, there we go. Yep. And the video will show Is that still showing on the? You can see it? Okay. All right, so I'll start from the beginning again, but I'll just give you a little explanation about what's happening here. So this is observing the I and Q channels that come out of the mixers and the low-pass filters. Now, if you recall, the I and Q are basically the XY components of the Cartesian plane, right? So what you should see on here, and in this oscilloscope, I switch between a rolling visualization and an XY plot. So you can see the actual signals in time, but you can also see them as a phasor. And I will show what happens as you change the modulation type. And you'll be able to see what's happening in the phasor, and you'll see the phase locking occurring because the beat frequency will disappear. So this is in lock. That's out of lock. And you'll see as it comes back in, it'll settle. That's the charge pump at work. So now it's reasonably well stabilized. It's in phase lock, and so now we've actually converted to baseband. There's a bit of an explanation about what's happening here with this phase shift keying. It should be 180 degrees out of sync, but there's a reason why it's not. I'll explain after. So I was just checking to make sure it was still in lock. Trying to work out what's going on. And to verify it, I changed to amplitude modulation. So amplitude modulation, you'll see. That's PSK. Now we're going to AN. Now it goes into lock. Right, so amplitude modulation is a change of the amplitude, of course, right? But there's no phase change. So there you go. Like to see it again? I'll show you the video one more time. And I'll tell you what's happening with the phase shift keying. And it's because I don't have a low pass filter on the loop. So what it's actually doing is it's tracking so quickly. I think this is what's happening. It's tracking so quickly that the reference oscillator doesn't stabilize. It's actually tracking the modulation, and that's why it's another 480 degrees. Because the loop is so fast, it's tracking the modulation rather than the carrier. Okay. Yeah, so a couple of points to note. As I mentioned, the pullability of that voltage-controlled oscillator, TCXO, is not really suitable for use as a receiver because you're just not going to track the wide range of signals you're likely to see in the carrier. The zero crossing, I did a bit of a botch job on that. It should have been done a lot more meticulously, and that ultimately is going to affect the phase performance of the loop. There should be isolation between the power supply and the reference. So it should really be a clean, stiff reference. The comparators should also be a lot faster. There should also be over voltage protection on them, because you just don't know what kind of signals you're going to be plugging into them. In quite a few demonstrations of the phase frequency detector, the digital PFD, they show a delay block. And there's also a lot of mention about trying to ensure that you don't switch both the current source and the current sink on at the same time. It turns out if you use transistors that are fast enough, you don't really need a delay. In fact, you end up with much higher performance. The other thing to note is when you're using a current sink and a current source, at the time where they're both switched on, and provided the current source and the current sink are matched, you actually have net flow of 0 into the capacitor. So it doesn't matter. So there's a lot of sort of discussion about, should we, inhibit logic and trying to make sure they don't short out. Well, they're not going to short out because they're current sources. So they're going to limit the amount of current that can flow through them. So there's no risk of short. Yeah, so where to now? I need a holiday. So I spent way too much time doing this over the last week. So I started this on Friday. Yeah.
You finished it this morning?
Yeah, I finished it this morning, which is why there's not a lot of text and lovely diagrams and pictures. It's just sort of dumping the pictures. Yeah, I consider my life choices too. Yeah. No, I'm a person of extremes. I tend to go from one to another, so probably going to Bender tonight.
You're saying the 0% detector.
Yeah.
Right. Is that as a general approach or just that particular approach you've got?
Yeah. So I've actually done a lot better job in the past by reverse engineering a frequency counter, like lift the tracks off the board and pass in my own signal. So I was very careful about that one, so I didn't want to fry a frequency counter. The way I did it with that particular one was I converted the unbalanced into a balanced signal, and then I used, right, so you've got, let's say for example, 2.5 volts peak. Let's keep it easy. 2.5 volts peak, right? 5 volts peak to peak. Oh, actually, no, it's not going to be easy. Anyway, so then if you pass it through a balun, you end up with equal and opposite signals. Right, so converting from an unbalanced signal to balance, right, you end up with equal and opposite. So you end up with two signals, but they're equal opposite in magnitude. The good thing about that is you can reference each one against ground. So ground, as a reference, you've got them both going above and below ground. You can put overvoltage diodes in them, so you can protect your input. You also have an enlarged voltage swing as a result of the use of the balun and the transformation in the transformer. And when I did that, I actually passed each arm of the balanced signal into one side of the comparator so that it triggered as they crossed over each other. So you don't actually need a resistive reference or anything. They're referenced against each other. Yeah. So that's the way I've done it before. But that requires a lot more thought, and it requires tuning of the transformer. And I just thought, nah, I don't have time. Might not be here with the result if that had been the case.
Thanks very much, Yuri.
Yeah, cheers.